Hello and welcome to Answer Everywhere. We're taking a look at some source code. That's what we do all the time. We do some sight reading of source code. Today we're looking at MimbleWimble, specifically the Grin implementation of MimbleWimble, which claims to be a minimal implementation. MimbleWimble is some sort of cryptocurrency protocol. I am not personally familiar with it. There appear to be some zero knowledge proofs, and it's in Rust, which I'm also not super familiar with, but I think is mostly pretty readable. So let's dive in. This was a request from user Philippe, and Philippe donated $1.50 to the channel. The way we do request scheduling is they happen typically once a month at the end of the month. And it's based on people who donate to the channel. And right now prices are low if you want to donate and get some open source project looked at. All right, I really have no idea, literally starting from zero on the mimbly-wimbliness of it all. I'm going to ask Gemini to explain it to me. Can I do this? Tell me about. Hello? Maybe not. Tell me about the MimbleWimble protocol. Assume I'm a cryptography expert who is skeptical of blockchain claims. Just to kind of get it the right tone, I'm going to say that. That's more or less accurate. I mean, I'm not anti-blockchain. I'm not anti-cryptocurrency. I have, however, been exposed to a lot of people. Hang on here. A lot of people who are very strongly pro-cryptocurrency. So I have a lot of experience hearing things that I don't believe and having to kind of tamp down expectations. Sorry about that. Bot Eater and Mrinal Batarai. I hope I pronounced that name somewhat close. So I'll start over here. Sorry about that. I had muted myself. I thought I had successfully unmuted, but I had unsuccessfully unmuted. Okay, so I think that we'll just start over here. So MimbleWimble is going to do a couple of things. It's got confidential transactions. So Bitcoin is the classic cryptocurrency, and it has pseudonymous transactions. So you can try to you can often track people across the Bitcoin blockchain, and if you are able to de-anonymize one of their, or ideally a few of their addresses, you can learn a lot about their spending, and that happens in like probably criminal court cases, possibly divorce cases with if a lot of money is on the line. And then so they've got the confidential transactions, and they've got some sort of transaction aggregation cut through. I don't know exactly what that means, but that's presumably going to be some sort of compression where the we record less per transaction. One of the annoying things about Bitcoin is it presumes that if everyone's going to verify the transaction, then they need to know all of the transactions ever through history, which is a lot. So a lot of the changes have been about reducing that load. And I don't know whether they're going to do that in a lossless way, or if they're going to take the information and put it somewhere else, or if there's a lossiness to it. And if Bot Yeeter or Mrinal, either of you know anything about MimbleWimble, let me know, because I have no idea at this point what I'm up to. Okay, so so we've got this Patterson commitments, or Peterson, I'm not sure how that name is pronounced. So instead of recording transaction amounts V in plain text, we're going to commit, we're going to send C, which is, we have VH here, so there's some operator H, and I don't know what space we're plussing in. G and H are two distinct generator points on a chosen elliptic curve. This one, that might be the Bitcoin one, I don't remember. SECP 256K1. Crucially, the discrete logarithm of H with respect to G, K such that H equals KG, must be unknown. Okay, so this is discrete logarithm problem. And V is the amount of value committed. So you commit, you're kind of obfuscating here the amount that you are sending. So V is the amount of value to be, yeah, we saw that. So R is a secret blinding factor, effectively a private key. So I guess if this is the private key, then you're really the only one who knows how to do this. I don't know if G and H are public. So hiding given C, G, and H is computationally infeasible to determine V without knowing R. Binding is computationally infeasible to find a different R prime, V prime, such that this relationship holds. I don't know just off the top of my head how to guarantee that, but basically what we're saying is that you have the ability, I guess, later to reveal what V is given R. And then there's some homomorphism property. If you have some two commitments, you can sum them together, and the private keys sum together and the values sum together. And I guess that's used for transactions, right? So this is crucial for verifying transaction balance without revealing amounts. The transaction is valid only if the sum of its output commitments equals the sum of its input commitments plus any explicit fee. Okay. So I don't know where the fee shows up. This is saying sum of V out minus sum of V in are balanced. Okay, and then we have some range proofs, typically bullet proofs. Since their homomorphic, a malicious actor could create outputs with negative values, that still balance the transaction equation. Yeah, that's money creation. Each output commitment must be accompanied by a range proof demonstrating that the committed value V lies in a valid range. From 0 to basically some positive number that fits in a 64-bit thingamajiggy without really revealing V. It seems like it says bulletproofs are commonly used, but I don't know if they are mandated by the protocol because they are non-interactive zero-knowledge proofs with logarithmically sized proofs and don't require a trusted setup. Okay. And then we have some transaction kernels and signatures. So the MimbleWimble transactions don't have traditional addresses or scripts. Ownership of a UTXO, which is what, like an output unspent transaction maybe, something, is proven by knowledge of the binding factor R, right? So that the R is your private key. And basically having the private key proves that you own the commitment. To authorize spending, the transaction includes a kernel. So we have some equation. The sum of C out minus the difference between C out and C in sums is equal to the, this is just the homomorphism, right? We're going to sum the output private keys minus the input, I guess, V's. Or something like that, because we have this G factor. Let the excess binding factor, blah, 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 be the kernel's corresponding kernel excess is R excess of G. Okay. The transaction kernel contains this public kernel excess, K, and a signature, typically a Schnorr signature, that proves knowledge of the private excess binding factor. The signature effectively signs the transaction details, proving that the creators authorize the transaction and that the values balance. Because if these differences are not zero, the commitment equation wouldn't result in a point solely based on G. Okay, and this replaces traditional address-based signatures. I don't really follow this, but I don't want to be this. I don't want this to be entirely just me reading this Gemini output. I want to at least get. I want to get a little sense, and then I want to get to the code, and then maybe go back and forth. And then these are the kind of like the features. We have private confidential amounts, no on-chain addresses, transaction aggregation, and cut-through. When transactions are included on a block, they can be aggregated. If output A is spent by input B within the same aggregation set, both A and B can be removed. I think this is just the kind of like the homomorphism property. If you're in the sum, they can cancel out, and what remains is the block set of all unspent commitments and the transaction kernels for every transaction. Then verification of the entire chain state involves taking the sum of all the UTXO commitments minus the sum of all historical kernel excesses. Okay, and then there are some privacy limitations and criticisms. There's some de-anonymization attack, I guess. The cut-through happens after transactions are broadcast and aggregated. An adversary monitoring the peer-to-peer network before aggregation can observe individual transactions. Okay, so it seems like maybe there's some like peer-to-peer protocol, and then the blockchain is a little bit separate. It's like a separate like finalization of the stuff that's going on minute by minute in peer-to-peer. And then by linking these, they can reconstruct the transaction graph. And this has been demonstrated by Ivan Bogati. Okay. So it's weaker than Zcash, which has shielded pools, and Monero, I guess. And there's some scalability benefits and so on and so forth. We have looked at, what, Monero, I think? So they use two separate, bot user saying, so they use two separate elliptic curves as a source generation, multiply them with the R private key, transaction the other source. I think they're using one elliptic curve here. And H and G are different generators of the same elliptic curve. Basically 2 points that generate the curve. Okay, so that's a little bit what's up with the crypto. Let's see now. Let's look at the code. I don't know what we will find. So P2P, I'm guessing, is the is not the crypto stuff, although who knows? I don't know if Etsy will be important. Core, I don't know. Chain will definitely be important in API. And what do we see here? Chat. So I guess they do their chat on Keybase, which I don't think exists anymore. I don't know how up to date this is. When was the last commitment? Last month? Okay. Does Keybase still exist? Maybe. Okay, so here's let's see. Here's P2P. We've got some fuzzing. Fuzzing is good, especially for a crypto thingamajiggy. You have to use Rust nightly at the moment. Cargo fuzz has been what used. Okay, so this was 6 years ago. You had to use Rust nightly. I don't know what that means. I guess that's like a nightly release of Rust itself. These are all several years ago. So in the P2P we have some codec, con probably connection, handshake protocol, a library, some stuff for messages, peers, and then this protocol.rs. I don't know what of this is important, if anything. Should we look at how big protocols is? Protocol.rs. Not huge. There's something about banned peers. I guess you can be banned. And if you get banned, they just drop your messages. So I guess you can't spend anything. But we'll look at that later. I think what they want to know, I think the requester wants to really know about the protocol, which I assume is the crypto protocol. In pool, we have lib transaction pools. So I don't know if a transaction pool is just the block of transactions. A transaction pool takes a blockchain and a pool adapter. It has a config, an actual transaction pool, whatever a dandelion stem pool is, and some cache of transactions, and the blockchain itself, and whatever a pool adapter is. I assume the pool adapter provides some functionality that might change depending on what, I don't know, options. And then we have, I guess, this is Rust. So this is a struct. This seems to be an implementation, probably. You can create a new one. It just seems to do some like memory stuff. We're gonna clone the chain. Wait, what? No, we're gonna clone what? Yeah, I don't know how expensive cloning a blockchain is. I don't really know what the blockchain keeps in memory versus what's on disk. And then we've got the stem pool stuff. Let's ask Gemini about stem pool. What is a dandelion stem pool? So we have the dandelion and dandelion plus protocols. There's a dandelion protocol is a transaction propagation mechanism designed to enhance user privacy by obfuscating the originating IP address of a transaction before it's widely broadcast to the network. So we've got a stem phase. When a node originates a transaction, it receives one, it doesn't immediately broadcast to all its peers. Instead, it forwards the transaction to only one randomly selected peer. Then the peer forwards it to only one of its randomly selected peers, and so on. This creates a linear path. And then a fluff phase, after a random number of hops along the stem, the node designating the fluff switches behavior. It stops the single peer forwarding and instead broadcasts the transaction widely using a gossip-like diffusion method. Okay, so this is like, sounds kind of like strictly weaker than something like Tor. We're not really going to hide the IP address if you have enough nodes. If you own enough nodes in this dandelion network, then you can just track everything. But the hope is that the number of nodes, I guess, doesn't correlate with the amount of money you have, which is, I think, empirically false. And who knows how popular this network is. So I would just assume that dandelion does nothing. Personally, if I was interested in some sort of strong anonymity. Okay, so transaction pools looks cool. I want to see something a little bit closer maybe to the crypto, So I have a feeling that's going to be a tar pit that drags us all in. In source, we have bin and build. Those look compile-y and buildy. It's a strange way of thinking about transactions. How so, bot yeeter? Core. Do you mean the dandelion approach? Or something else that I said? Consensus. So we have consensus. I don't think Gemini talked about how consensus works. I guess the consensus probably works more or less the same. And they were building something like a Merkle tree, perhaps. Then here's chain, and here's API. I don't really know where to be. So let's just let's look at API maybe. So API has auth. I'm guessing this is like client auth. Foreign. Handlers, JSON, RPC. Let's look at JSON, RPC. Let's look at lib. I don't know what owners is. REST is presumably maybe like a REST version of the API. We have a router, types, and we have web. So is there a web front end? What is this called? Grin? There doesn't seem to be an obvious screenshot of like a web front end. Okay, so here's a JSON RPC thing. We've got responses. This looks like standard RPC kind of handling. We have an error type. More error handling, standard error. This doesn't look like it's defining the protocol itself. This seems more like just kind of like setting up the ability to receive messages and send messages. We're sort of rolling our own RPC structure thing, and we've got CERD for serialization, deserialization. All that's probably fine. lib.rs under API. Who knows? There's not much here. Mainly, we've got some, I guess, like acknowledgement of other, whatever they're called, modules, libraries, sub parts of the project in Rust. Owners. Create a new API instance with the chain, transaction pool, peers, and sync state. All subsequent API calls will operate on this instance of the node API. I don't know if this is called owner, but you can create a new chain. You can validate the chain by calling chain validation handler validate chain, invalidate header, and so on, get peers. This is kind of like a control point, I guess, unban peer, ban peer. Bot Eater is saying they find the dandelion one weird because it thinks that the value of the transaction is based on the number of... I don't know if it's the number of blocks. I think it's more like... Because it's supposed to be pseudo-anonymous. Like, let's say that you're just an ordinary person and you have like a laptop or whatever with an IP address that doesn't change a lot. They don't want you to be able to trace all of your transactions to your home or laptop. And let's say you're doing crimes on the MimbleWimble protocol, which I do not advocate. But let's say that you have some ISP, you pay like Comcast or whatever, and people notice that a lot of the crime, a lot of the, people notice that when the what's the Dread Pirate Roberts thing? Somebody selling marijuana on tour, and they noticed that based on the traffic that when the transactions happen, they're being sent from your IP address. Then they can just subpoena like Comcast and figure out where you live and go talk to you. So that's a way that, like, even though the blockchain might seem anonymous, if they can determine that your IP address is sending a lot of these anonymous transactions, then that's a way to get information about you. So they're trying to limit that by having this like kind of like friend of a friend mode initially, where it's not just one IP address that's broadcasting all of your crime transactions, but it's not like it's not like super well thought out. It's not a strong privacy guarantee. It's more like a something that will work on average, which is typically not what you want for security, but probably better than nothing. This is owner RPC. I think this is not going to be so important. This is REST. I guess this is maybe really about like a front end or a proxy. We've got some TLS config, like a reverse proxy sort of thing. We have an API server implementation thing, and you can tell it whether to start without TLS or probably tell it to start with TLS, like here. Okay, so this is kind of not fundamental to the protocol. And then router, we're going to do it by HTTP verb, which I thought typically you do this by path. I guess there's no reason you can't do it by HTTP verb. Okay, so this is not really fundamental. And then we have some types. A tip, the state of the current block, fork tip, the current fork tip. I don't know if we consider every non-committed block to be like a potential fork. So I don't know what fork means here. But we have some block height. The last block pushed, maybe the hash of the block, it's some sort of string. Previous block to the last one, this is like the penultimate block. And then the difficulty accumulated in the fork. And then given the tip, well, given a tip, you can call from tip, I guess, and get a new tip. I don't know what that means. And you've got some status, which has a chain, a protocol version, a user agent, and so on. Yeah, I think that's right. But the idea is that like to traverse the list of anonymous calls, you have to control enough nodes to kind of be the entire stem of the dandelion, which is probably not too hard. You just rent a lot of VMs on AWS or whatever. Okay, and I'm pretty sure that web is not going to be where we want to be. So where do we want to be? Maybe core? Maybe consensus. I don't know what POW is. Maybe libtx. So in consensus, I see a bunch of height stuff. Cut through horizon. These are like constants. These are all like setting up constants. This is something to I guess compute the header version. Something about graph weight. Compute weight of a graph, number of SIP hash, etc., etc. Okay. What is POW? Cuckaroo. The Cuckaroo cycle context only includes the verifier for now. This is now looking interesting. And whatever libtx is, mod, reward, proof. Proof? Create a bulletproof. Okay, that is definitely interesting. In core, we have block sums, committed, compact blocks, hash, ID, Merkle proof. These. Give me 1 second. All right, so we're finally in a place that looks like we have cool stuff. I don't have a lot of time, but we'll see what we can see. This is kind of like something that's a little bit complicated. All right, I have no idea what Kuckaroo is going to be. Let's see if we find any hits for Kuckaroo. Kuckaroo. There's a cuckoo miner. So cuckoo miner is a Rust crate which provides various implementation of the cuckoo cycle algorithm. It's primarily intended for the Grim/MimbleWimble blockchain's proof of work system. Okay, cuckoo cycle. Yeah, the robin. That robin. I don't know if it's related to cuckoo hashing. Cuckoo cycle is some white paper. A memory-bound graph theoretic proof of work. We introduced the first graph theoretic proof of work, 2014, based on finding small cycles or other structures in large random graphs. Such problems are trivially verifiable and arbitrarily scalable, presumably requiring memory, linear, and graph size to solve efficiently. I don't know how much work that presumably is using. So this is, I guess, this is some algorithm to find graph cycles in random graphs. The graph cycle finding algorithm uses 1 bit per edge and up to 1 bit per node. Runtime is linear in graph size and dominated by random access latency, which they say is good for a proof of work. Okay. So that's probably what Kuckaroo is doing. Let's see if we can verify that. So we're using this PAL stuff, including cuckoo parameters. Oh, PAL must be proof of work. I thought it was something about computing powers of the elliptic curve, but it's not. Instantiate the new Kuckaroo context as a PAL context. Note that this can't be moved to the PAL context trait. Okay, so this is some, just create a new context, and this is more context stuff. I don't really know what we're doing. This is, we are iterating over something. We've got this edge masks. This looks like it's part of the algorithm, but what is this function? Oh, this is the verify function. Okay, I was just not reading the Rust correctly. Okay, so to verify, it's a proof. And the proof is some, I guess, claim that there's a some number of cycles in the graph, or rather, the proof should be both a claim, namely that there's some number of cycles, and also like a description of what all the cycles are. And somehow we're going to verify that that's the case. And we've, I don't think it's really going to help to go through this algorithm. For the one thing, I don't know enough about the Rust syntax to be sure that I know what every data structure is. Obviously, this is some sort of vector, like a linear outlay of memory. We are going to iterate over size. Where did size come from? Size is the proof size. I don't know if that's presumably that's the number of elements in the proof. And if it's not equal to the global proof size, then we have the wrong cycle length. Okay. And so we're going to get the proof nonces. These should just be like disposable numbers. By the way, I'll try removing the Robin noise when I post these. So for people got confused recently, maybe it was, so typically what I do is after I record a live stream, I mark it unlisted so you can still watch it if you have the URL, but then I post a slightly edited version. And I'll see what I can do. See if the AI sound stuff will remove robin noises. I don't know if they will. And sometimes like the AI, like the NVIDIA broadcaster thing, make you sound like pretty robotic. So I don't always use them, but I'll try that out, and hopefully the posted version will have fewer robin sounds. But I wanted to say that just in case people who are watching this live stream are confused when it becomes unlisted for a few days. Okay, so we're getting heads, previous, blah, blah, blah. Something about masking. Whatever a SIP hash is presumably some kind of hash. And then we're going to just verify the cycles. And it's probably not a difficult algorithm. In fact, it looks pretty simple, but I'm just not going to really go into it because among other things, I want to see more of like, what is this proof type? Where is it? This proof. What can I find about this? Proof. It's in types. But where? Move this chat away for a second. Is a proof just a string? I don't know if I believe that. I don't really know what syntax to search for to find the actual proof. Maybe like struct proof? No. Okay. Well, it's not coming up in an obvious way. Maybe it is just a string, but I doubt it. Here's consensus. We've got something about graph weight. Compute the weight of the graph as a number of SIP hash bits. Let's look at what his SIP hash is. Secure pseudo-random function. It is an add, rotate, XOR based family of pseudo-random functions created by Jean-Philippe Almason in DJB, Daniel J. Burstein in 2012. Okay, so this is a presumably a well-respected and probably fast to compute hash function. Wait, hash function or family? Family of pseudo-random functions. All right, and we're using them here. I'll just think of it as a hash function. We've got this graph weight. Compute the weight of the graph as a number of SIP hash bits defining the graph. The height dependence allows a 30-week linear transition from C31 plus to C32 plus starting after 1 year. I don't know what that means. So this is checking the height, whether it's 31. I guess that's what this is. And whatever expiry height is. And then we're doing some shifting. We've got this 2U64 thing. We're left shifting. We've got some edge bits minus the base edge bits. Okay, so we're just doing bit counting, which I think is what this is saying. And then there's maybe some weird stuff here that's about whatever that is. Minimum solution difficulty. After hard fork 4, when PAL becomes primary only, KUKA 2, 32 plus. So I think this 32 and 31 is something about like a global parameter, possibly related to the difficulty or to the proof size. And this maybe is a transition due to a hard fork, either based on an attack or based on growth or something else. This is some stuff about header difficulty. Let's see if we can look at the functions and see if there's something that looks especially important. We have rewards. power ratio, and so okay. Header difficulty. Okay. I don't know what in there is important, but we're going to move along. Here's proof.rs. Maybe this was the place I wanted to be. So you can create a bulletproof. You pass in K and B. I don't know if these are the, I don't know if K is the amount you want to spend, although there is amount. And we have an identifier, which is some key ID. And a switch. And we've got a keychain and a proof build. I don't know what a proof build is. Oh, K and B we're parameterizing by them. So K is a keychain, which will presumably, the key ID will presumably be an identifier for a key in the keychain. And whatever a proof build is. And we'll get this elliptic curve, I assume is what SECP does. And then we'll call commit, passing in the amount. Here I assume that this is computing basically this, where V is the amount and R is the key indicated by the key ID. I don't know what switch is. Proper support for different switch commitment schemes. Okay, and then we're going to get a key that we get by on the keychain doing some key derivation, passing the amount in the key ID, and again switch. I assume the question mark is like nullable. We've got this rewind nonce. I don't know what rewind nonce is. And a private nonce. And proof message. Okay, so these are some nonces that come from B, where B is the proof build. Whatever the proof build is, some sort of thing that has information about nonces, for example. Presumably has some sort of random number generator. And go away. And then we call OK. I'm guessing OK is going to check the result of whatever this function is. So we're going to call on SECP, which is essentially the elliptic curve, I thought, but maybe not. It may be more than the elliptic curve, but we're going to call bulletproof, passing in the amount, the S key, the rewind nonce, the private nonce, and the extra data. And sum of message, where message is the proof message. And then we've got verify. And to verify, we ultimately call it the SECP verify bulletproof. So we are using bulletproofs, as Gemini suggested. Rewind. Seems like we're doing some work to find here. We're going to get a rewind nonce, possibly error out, and then call SECP rewind bulletproof. And then proof build is, I guess, defined here. Yeah, I don't know about Yeater. I don't know. So used for building proofs and checking if the output belongs to the wallet. So we're going to create a BP nonce that will allow us to rewind the derivation path and flags. So allow us to rewind the derivation path of flags. I don't know what or why, but that's a thing. And then we can create a BP nonce that blinds the private key. So that should be the blinding thing. Oopsie. Here. Where did blinding go? Here. Or, I don't know. This is saying blinding seems to be a feature of the commitment itself, but maybe there's another step, or maybe this is computing something that's needed for the commitment. And then what? And then we have the ability to create a proof message and check the output. And here, this is a trait. This is now a struct. I don't really know how they are different. I guess struct seems more concrete. Are these the same, called the same thing? Oh, proof build versus proof builder. Okay. New nonce keychain, rewind nonce, private nonce. Here's an implementation of proof message. So message bytes, 0 is reserved for future use. 1 is wallet type. 2 is switch commitment type. 3 is path depth. And 4 to 19 is derivation path. So we're going to create just like a vector, some slice of memory to record the message. Message 2 will be switch commitment type, whatever that is, some number. And then the ID bits, we're going to take the ID, make it into bytes, rather than bits. And then for a 3 to 20, we're going to take the ID bytes. And then we're going to call proof message from bytes. So what? So where does the actual computation of the proof come from? It comes from ID, the identifier. And here, let's go back to the top here. It's just the key. The key ID. I don't know what that means. Does that mean that we are identifying keys by a bunch of bytes that indicate some proof? I'm not sure. But let's look at check output. Check output, we'll look at the message length. We'll take the message as bytes. We've got some, presumably this is going to be used as an exponent. Some of the stuff from 0 to 2, I guess. And possibly error out depending on what's in the first little batch there. We're going to get the switch commitment type by just looking in the message. We'll get the depth by looking at message 3. I have no idea what that function does, honestly. And then the ID will set the identifier from serialized path. Yeah, so I guess the thing that is the ID is also a serialized path. So it seems like we're using the path. The path is the proof, I think. And it's also the identifier for the keys, if I'm understanding correctly. And then we have the self keychain commit with the amount and the ID. That gives us the commit exp. Maybe expected instead of exponent. And then we check that they are the same. Okay. Fine. But now I need to know what from serialized path is. Okay, from serialized path. Where are you? So these are just calls to from serialized path. Again in types. From serialized path. ID is going to be something from 0 to identifier size. 0 is just the length. And everything else, we're going to clone from the slice of P and make that an identifier. This is just moving bits around. So that's not so interesting. Serialize a path, output the path itself for insertion into bulletproof. For this, whatever self is, we'll sometimes GitHub will tell me like up here what we are part of. But it doesn't seem to understand enough about Rust or this repo to do that, but we can scroll up and find it. Okay, so to serialize a path, we've got whatever self is, and we're going to return some stuff, some like vector of some size. And the return value, we're going to take the size -1 and 0 as a, I guess, unsigned 8. And then we're going to just do copy from slice. So what in the world? So this is an implementation of identifier from path. Okay, so the path itself is a bunch of bits. It seems like that's consistent with what we saw about, what was it, like the cuckoo algorithm? It seemed like they were going to take a random graph. I don't know how the random graph is laid out in memory, and they're going to have some proof of cycles. And it seems like the thing that algorithm returns, or whatever algorithm, is going to be a bunch of bits. And I don't know what those bits represent. You can imagine if you had like a tree, like a walk down the tree, you could represent by a bunch of bits. Like a 0 might be, if it's a binary tree, a 0 might be left and a 1 might be right, and a bunch of 0s and 1s would give you a path through that tree. This is in general a random graph. Maybe instead of each bit representing a step, maybe a byte represents some sort of choice, and you have a known starting point. Maybe you have like maybe you serialize the graph with something like in order traversal, or some traversal, and then I don't know. There are lots of ways this could go. I just don't know how it is going, or if any of them are even close to being correct. We have a secret key. Return the identifier of the secret key, which is Blake B, a 10-byte digest of the public key, corresponding to the secret key provided. Okay, so the identifier of the secret key is a hash of the secret key. I hope that's not public. You do want it to be deterministically determined by the key. That's good. You probably want something else mixed in there so that it doesn't potentially leak information about the private key. So since the path is just random bits, they try to detect bit patterns and show a cycle in that. Sounds too mystical. I don't know. I mean, maybe we can find out. But let's kind of move along here. We have Merkle proofs. IDs. Did we just look at IDs? I don't know. I don't know what permers is. I think we opened the other stuff. ID, short identifiable for age, blah, blah. Yeah, I don't know. So let's try to find this out. This is stuff about blocks. I want to see if there's something I've already opened up. Block sums, you know what I'm going to guess is going to be simple. Once we know, once we have the right types defined, we're just going to sum up blocks. And the kernel stuff, based on what Gemini was telling us, is probably pretty simple. I don't know what committed is about. Just going to check the kernel excesses and some commitments. And this should now just be adding and subtracting things. And we're going to verify the kernel sums. Leave that open. Compact block. I'm assuming compacting might just be removing things that are canceled out, but who knows? Sort everything. Lightweight validation. Verify everything. Stored in lexicographical order and no duplicates. Okay, so we're going to sort, remove duplicates, and then compact representation of a full block. Each input-output kernel is represented by a short ID. A node is reasonably likely to have already seen all transaction data. Okay. So this is somehow like just compressing stuff. Hash is what? A hash consisting of a blah, 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 and not, and we looked at IDs. And then Merkle proofs. I'm not sure. I know what a Merkle tree is. I know what some other Merkle stuffs are. I don't know if Merkle proof is related to Merkle trees or something else. Well, the word tree doesn't appear anywhere. I'll ignore that for now. I don't know what PMMR is. Persistent and prunable Merkle mountain range implementation. For a description of Merkle mountain ranges, look at this stuff. Okay. So I don't know what is what of this stuff is being used and what is not. It seems like we are doing bulletproofs. And here's the cuckoo cycle thing. Maybe we'll look at that. Let's see if we can find stuff about bulletproofs. Short proofs for confidential blah, 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 blah. I want like a more authoritative source, which I misspelled at Wikipedia. Maybe Stanford? Or short, non-interactive, zero-knowledge proofs that require no trusted setup. A bulletproof can be used to convince a verifier that our encrypted plaintext is well-formed. An encrypted plaintext is well-formed. Okay, for example, that an encrypted number is in a given range without revealing anything else. Compared to snarks, they require no trusted setups. Okay. They're designed to enable efficient confidence transactions in Bitcoin and other cryptocurrencies. And it seems like these are, we've got some Stanford people, some College London people. Dan Bonet is on it. So maybe this is a real paper. Is this the paper itself? Maybe. Okay, so how do they work? There's some multi-party computation. They implemented an MPC protocol whereby distributed proofs of multiple provers with secret commitment values are aggregated into a single proof before the fiat Shamir challenge is calculated and sent to the verifier, thereby minimizing rounds of communication. Secret committed values will stay secret. Okay. So we're somehow pulling together information, it looks like, from multiple provers in a secret way. And then we're doing kind of the, I think fiat Shamir is just like the standard MPC thing. Whoa, 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 whoa. Whatever that is. Go away. Yeah. Okay, so fiat Shamir heuristic is a technique for taking an interactive proof of knowledge and creating a digital signature based on it. Okay. So I guess I'll review this. And the essence of bulletproofs is its inner product algorithm, originally presented by Groth, and then further defined by Boodle. The latter development provided a proof argument of knowledge for two independent, not related binding vector Patterson commitments that satisfied the given inner product relation. Bulletproofs build on these techniques, which yield communication-efficient zero-knowledge proofs, but offer a further replacement for the inner product argument that reduces overall communication by a factor of 3. And then it is used in MimbleWimble. So the basis of confidential transactions is to replace the input and output amounts with Patterson commitments. It is then publicly verifiable, the transaction balance, etc. We saw this. I guess Gemini summarizes this. A prover must convince the verifier that the commitment CXR, which is the sum of XH and RG, contains a number in some range, which we saw. As part of the ensuring protocol, the verifier sends random linear combinations of constraints and challenges to the prover. I don't know where the challenges come from. I think this is non-interactive, but they're going to send random linear combinations, and I guess that's enough to show that the things that we're combining with are in the appropriate range. The prover is then able to construct a vectorized inner product relation containing the elements of A, the constraints and challenges, and appropriate blinding vectors. These inner products have size n that would require many expensive exponentiations. The commitment scheme allows for the vector to be cut in half and for the two halves to be composed together, each time calculating a new set of Patterson commitment generators. Applying the same trick repeatedly, log2 of n times produces a single value. Okay, so I'm not really sure entirely what's going on. Intuitively, we've got this we've got this problem that we can break down in a kind of divide and conquer way to get this log behavior. And fundamentally, it seems like what they're doing is, in order to show that that the number that you're spending is, for example, non-negative, there's challenges that come from where, who knows, where you're just going to take this. Wait, what is the number x? I think what it's saying. Oh, hang on. No, I missed this sentence. I glossed over it. The basic idea is to hide all the bits of the amount in a single vector Patterson commitment. Oh, okay. So we break x into bits here, and then we're going to hide them all in a single commitment. And then you're going to prove that each bit satisfies that omega minus 1 is 0. This is what I get for trying not to read the whole paragraph. Each omega is either 0 or 1, and that they sum to x. I don't know what omega came from, or is this a w? Either way, I don't know where w came from. But we're going to break it into bits, and we're going to prove and use this commitment scheme, and we're going to try to show that that all of the that everything is positive, that they sum to the thing that we claim that they sum to. And then we're going to somehow do this with linear combinations in constraints and challenges, and then we have this this kind of log behavior. Bullet proofs rely only on discrete logarithm assumption. I assume the assumption being that discrete logarithm is hard. In practice, this means that bullet proofs are compatible with any secure elliptic curve, making them extremely versatile. And they're short. Okay. So we'll have to read this. Yeah, inner product is dot product. I think I consider them the same. The dot product might refer specifically to the R3 standard inner product. But yeah, you just take the components of the vectors. But given any vector, you can define an inner product with it. And I'm not sure which one they mean. I'm assuming that it might be a general inner product. But I don't know. Okay, so I'll read this MimbleWimble thing. I haven't read it beforehand. Here's the bulletproof paper. I guess I'll read that too. This might all be the same paper. And then we have this cuckoo cycle thing. Okay, so we are using bulletproofs, but that's different from, but what are we bulletproofing? And are we using both bulletproofs and the cuckoo thing? Do we need both? What consensus algorithm is MimbleWimble/Nguyen using? Understanding that MimbleWimble is privacy-centric, does it use zero-knowledge proofs to achieve privacy goals? Yes, zero-knowledge proofs, specifically range proofs, possibly bullet proofs in the future. And then Nguyen uses Nakamoto consensus proof of work with the cuckoo cycle proof of work system. You can find more information here. So how's cuckoo cycle being used as proof of work? I guess the double spin problem is somehow detected through cycles. Theoretically, Nguyen will scale better than Bitcoin, blah, blah, blah. However, cuckoo cycle itself contributes very little to the scalability. Let's ask Gemini. I think we did ask Gemini about the cuckoo cycle, right? No, we asked about dandelions. What is the cuckoo cycle in relation to MimbleWimble? Brain exploding. Yeah, this stuff is kind of hard to wrap your head around, because there are lots of white papers. It's unclear, kind of at the time, it was unclear what the status of any of the stuff was, whether people were like overhyping their results, and then there were a bunch of different people trying to work out different approaches. So there's a lot of kind of context to load in, especially even though it's like 10 years later. I'm not even sure how much MimbleWimble is still being used. Cuckoo cycle is a proof of work algorithm. Similar to the hashing thing, it's memory bound. Yeah, it's a graph theory problem. And they want to be ASIC resistance. I think that's related to being memory bound. Although it seems like you could just make a chip that has the appropriate memory cells. The gain prominence in relation to MimbleWimble's primary, because Nguyen was the first, it is not intrinsic. But it doesn't actually tell me what it does. So how does it actually prove work? Oh, I guess. Oh, I see. So proof of work. I was thinking consensus. So proof of work for the SHA-256, you want to show that you are spending compute time by doing SHA-256 essentially as busy work. And the cuckoo cycle is essentially being used as busy work as well. So there's not really anything to, I guess there's not anything really new to understand there. FPGAs for the win. It sounds like I was very far with this cuckoo cycle. Totally something else. Yeah, I think I misunderstood what it was up to. I thought they were using it as I thought that they were using it as a proof. As a proof thing. But you know what, the way that I was thinking about it doesn't actually make any sense. In fact, I remember when somebody was telling me about the Bitcoin for the first time, they were like telling me about the proof of, hey, where did my they were telling me about the proof of work algorithm with SHA-256, and I thought that was silly. And my first thought was like, why don't you just use a like a graph-based proof of work algorithm? In theory, you can use kind of any hard enough problem, and cycle counting, I guess, works. What is the computational complexity? Counting all cycles of length k can be achieved in O of VE time. Counting all complete subgraphs or cliques can be achieved in O n to the k squared in the general case. I'll ask Gemini. Tell me about the computational complexity of the cuckoo cycle algorithm, I guess. And so I guess when I was looking at the proofs in the code, those are not proofs of cycle stuff. Those must be proofs of those must be like the bullet proofs. Somehow information about the commitments that is proving that that the secret numbers are positive and bounded above by like 2 to the 64 minus 1 or whatever. So the core task, the algorithm aims to find one or more cycles of a specific length, L, in a large, so 42 is used in Nguyen, in a large randomly generated bipartite graph. It typically has n nodes on each side for a total of 2 times n nodes and m edges, where n is large, like 2 to the 30 or more, and m is usually close to n, often around 90% of n. And the asymptotic analysis, standard graph algorithms like DFS can be used for cycle detection. That would be O of V plus E, which is about O of M. And the practical bottleneck is the memory bound. So I guess it's the space complexity that they're worried about. This is the crucial point where the number of operations might scale linearly with n, but the actual time taken is dominated by memory latency and bandwidth. Okay, the blah, blah, blah. So the space complexity. This is Gemini knew what I really should have asked. Might also take over n space, but n is large. Is this really right? It's basically linear but with a large constant factor. Is that really the idea? So basically it's linear and a large constant factor. Something went wrong. Hey, I've reached my limit. I thought I paid for this. Maybe I paid with my other account. I'll say, tell me about bulletproofs in cryptography. And make the explanation cool as hell. Gemini doesn't know how to make something cool. All right, now I'll make the explanation dry and terse and mathematical for a mathematically sophisticated audience. Okay, so we want to prove it's in this range. We saw this before. A core problem is the efficient construction of range proofs. A standard approach involves proving that the committed value can be expressed as an inner product of a bit vector, b, and a vector of powers of 2. Okay, so these are kind of like sending this. I don't know how to think about this, but I think about this sort of thing a lot. Is kind of sending them into different spaces or like stratifying the vectors, or it's like the power system, right? Powers of 10, positional notation. Okay, so this is just essentially the BI and positional notation. The challenge is to prove this relationship and that B is indeed a vector of bits in zero knowledge and with a compact proof. What else could it be? As opposed to that they're all ones and zeros as opposed to like larger, I guess, because they can't be smaller. Bulletproofs achieve this succinctness primarily through a novel inner product argument. Given commitments of two vectors, A and B in IPA, not the beer, the argument, allows a prover to convince a verifier that the inner product of A and B is C for some public value with proof size 0 of log n, where n is the dimension of the vectors. Okay, so given commitments of two vectors, I don't know what the two vectors are, but suppose that we have two vectors. And we're going to show that their inner product is C. I don't know if the two vectors are supposed to be from the same transaction or if they're supposed to be from different transactions. Somehow I lost my chat here. There we go. You go to jail. All right, in the context of the range proof for a committed value V, let's say that it's VG plus, we've changed the variable names just because we're in a different chat now, where G and H are elliptic curve generators. Gamma is a binding factor, or rather a blinding factor, and V is the secret value. Proving that V, so V here, I guess, is what we were previously calling K, the thing that is essentially a price that we want to ensure is positive. It's transformed into proving properties about the binary representation of V. Yeah? Specifically, V is given this binary representation. The condition that that each BI is in 0, 1 is equivalent to BI times BI minus 1 is 0 for all I. Yeah? So the bulletproof range proof constructs vectors and commitments such that the validity of the range proof is reduced to verifying an inner product relation involving these vectors and commitments. So you're going to represent this as algebraic relations, which is not hard to do. And then they're going to encode them as a single inner product equation, which should also be not hard to do. You kind of just have to write down the thing. And then we're going to use a Peterson commitment to the value of V, and additional commitments related to its binary representation. And then we're going to apply the IPA recursively to prove it correct. Okay, that gives us some more information. And I think I'm going to stop there. I find it, Bot User is saying, I find it hard to rationalize the product between one bit, between bit 1 and the PAL2 one. Since one is just one bit of information, the other one is a whole number. And the PAL2 one. That's a good question. This is one of the things that if you were to like formally write down some of this stuff, it would be a little bit confusing because implicitly we're kind of moving in between spaces. For example, here, where V is equal to the sum of the BI times 2 to the I, it's different from here, where we say that B is, by definition, a string of ones and zeros. What they really mean is we're going to take this. What they really mean is that B is in some vector space. Let's say, an n-dimensional real vector. Well, we know it's not a real vector. We know it's at best a vector of integers. We know at best it's a vector of integers that are smaller than like whatever 2 to the 64 minus 1. And what we want to say is that there's some sort of projection from that vector to the space of ones and zeros. That is, if you do a round trip, that you get back the original vector. You don't lose anything. And to be able to say that projection round trip exists is that's how we, in order to prove that is possible, we kind of go through this process, which is that we multiply everything by 2 to the I, etc. So, I mean, we can ask like, let's just ask this question. So you defined let's see. Basically, you defined B as a string of ones and zeros. And then you say you want to prove that B is a vector of bits. What other possibility is there? And this might force it to say something like a little bit cleaner. This is an excellent point, and it highlights the crucial distinction between a mathematical definition and a description and what needs to be cryptographically proven. They say that B as a series of bits is the intended property of the vector that the prover claims to hold. However, in a zero-knowledge proof setting, the verifier does not see the vector B. The prover holds B as their secret witness. They receive a commitment to the value V, which the prover claims is formed from B in a proof. The verifier needs to be convinced the prover isn't using a vector B prime, where some B I prime is not in 0, 1, but could still satisfy the equation B I prime to the 2 to the I. So -1 may be an example. Consider a simple example. Proving a committed value V is in 0, 3. The allowed bit vectors are these. 0, 0, 0, 1, 1, 0, 1, 1, corresponding to values 0, 1, 2, 3. Okay. The vector of powers of G is 1, 2. If the prover could be using non-bit values, they might use B prime is equal to 3, 0. So here's, I think, the answer, what your question is getting at, which is that now we have a B prime that is not just bits, not a string of bits, I guess, in the sense. in the sense that it claimed B was. Then B prime G is 3 times 1 plus 0 times 2, which is 3, which is in the range. Or they might be using B prime equals negative 1, 2. So it's not that being a string of bits is like a constraint on B. It's just that we want to, whatever the type of B is, it's really like bytes or something. And we want to ensure that each byte is 0 or 1, rather than literally being a string of bits, I guess is maybe one way to think of it. At any rate, I'm going to stop there. I learned a little bit about MimbleWimble. I don't think that I have accurately explained anything about MimbleWimble, but we've explored it. And it's interesting. All of this crypto stuff I think is interesting. I wouldn't mind learning more about it. I'm by no means an expert in the Bitcoin crypto space, but there's some cool stuff. Will crypto eventually take over? I don't know, but we'll see. But I will be back next week. Thank you for watching. And Bot Yeater says, I finally get it. There's a lot of strange way to use inner products to prove you stay on your. Yeah, it is cool. I mean, people. The fact of the matter is, people talk about it in a sloppy way, and this is a thing that I've noticed. No offense to computer scientists, this is a thing I've noticed with computer scientists. I would bet that when computer scientists read math papers, they have the opposite complaint, which is that if two like really closely related things in math are technically a little bit different, they'll often be described as being in like different spaces or with different notation. Even though the mathematician thinks about them as like almost exactly the same thing. And there are cases where mathematicians will identify things that are like really close, but not quite. But if you want to say all of that clearly, that's what some of the like homotopy type theory stuff is, where you have a way to either explicitly say that two things are equal, like two things are the same object with under different representations, or that they are equivalent under some equivalence operation, and you have like a kind of a proof of their equivalence. That's sort of where that kind of stuff comes from, is wanting to be able to explain to a computer that these two things are more or less the same, even though they look a little bit different, or vice versa. Anyway, thanks for watching.